Hello, everyone. For those of you who don't know me, my name is Brenda Rubenstein. I'm the Joe COUSTIC Family Assistant Professor of Chemistry at Brown University, which is a university in the smallest state in the United States, Rhode Island. I'm really glad to be here for MULTIPEAK. It is super early in the morning, 4 o'clock in the morning here, but we're going to get this done, even though it's COVID times. I greatly appreciate you taking the time to check out this talk. I'm glad that you're well enough to actually do that, given all the tumult that's happening. So today I'm going to take this opportunity to talk to you about some of the work that my team at Brown has been doing over the past few years on trying to encode information in and compute using small molecules. So many of you are probably used to thinking about encoding and computing using molecules, but using molecules that are really polymers, things like DNA, things like RNA. DNA and RNA have their clear advantages, but we're really interested in looking at small molecules because of the fact that they are more dense. So you can show that small molecules can store information at an even greater density than DNA. It's tough to do, but it is in fact possible. Small molecules also offer new means of actually encoding information and computing. So small molecules have many degrees of freedom that you could potentially access. And using those degrees of freedom would allow you to store more bits per molecule. One can also think about the basic operations of small molecule chemistry as being reactions. And small molecules have many more different types of reactions, many more different flavors of reactions than, let's say, the standard polymers that we tend to think about. So small molecules offer some opportunities in both encoding and in information processing, and we felt really excited to try to see how much we can do using these small molecules. So the story I'm going to tell you today is about small molecule chemistry, small molecule information processing, and during the course of this story, I'll try to highlight the differences between small molecules and polymers. So you obviously can't ask me questions live, but feel free during the subsequent session to ask me any questions that you may have. I know that this kind of encoding is a little bit different. So with that all said, let me share my slides and I'll get started for today. Okay. So today we'll start out with maybe the simplest thing, which is the motivation for doing all this. And I think many of you are probably familiar with this motivation, that molecules offer you a way of encoding information and information processing that's more dense than our typical systems. Small molecules also enable us to do computing with much lower energy uses. So I'm not going to go through all the details today, but I think you can easily do a back of the envelope calculation about how much energy is required to actually perform reactions and see that that's actually true. Once I go through the motivation, I'll talk about how we actually perform our small molecule storage. And just to be clear, this is different than how people usually store information in polymers. When we're storing information in small molecules, we're actually using disordered mixtures of molecules to store that information instead of the actual sequence of a polymer. If I have time, I'll talk about some molecular computing examples. We have many examples in the group, but I'll probably have time to talk a little bit about molecular perceptrons. And then at the end, I'll very briefly discuss where we're at and what are the outstanding questions. Now, what I should also emphasize before I go into this work is that I didn't do all of this myself. So I'm a theorist, and I thought of a lot of the original ideas that set this up. But this really wouldn't have been possible without the help of a lot of excellent engineers. So Jacob Rosenstein, Sri Freda, Chris Rose, who really knew information theory. And then also, we're just excellent engineers. I'm a theorist. I don't do things that are super practical all the time. But engineers, they see a task and they get it done. And so they were really helpful with things like automation and actually doing the chemistry. I should also say I should thank the synthetic team for making a lot of the molecules that we made. So Jason Sillo and Unsa Kim helped a lot with the synthesis. Okay, so what's the motivation for all this work? Why would we actually want to use small molecules? Why would we want to use chemistry whatsoever to store information and to process it? So my motivation actually goes a little bit further back. I have some personal motivation for this. And so the motivation for this, in my opinion, actually starts with things like this Fujitsu Facom 655 line printer. So this was an awesome printer for those of you who may have had it. Maybe you guys are as old as me and you might remember these. It was so awesome because it satisfied the need for compactness, great compactness in computers. Right? This thing was super compact for its time. And in fact, it was so compact that people like me actually used to hide in these things. It was my favorite hiding place as a kid. We had these in the basement, and I would open it up and hide inside the little cabinet. So these were super small for their time, but obviously super small for their time is not small for our time. So accompanying these kinds of printers were lots of magnetic tape. These also filled my basement, maybe probably my parents' basement until like 10 years ago. And so these things were incredibly useful, but not small on our scale today. Of course, it could be worse, and I can take you back even further. So here's actually my grandfather. My grandfather was a programmer for the UNIVAC. He's one of the mathematicians on UNIVAC. In 1952, he actually correctly predicted the US presidential election using the UNIVAC. But as you might recall, the UNIVAC at Remington Rand took up the entire room. It was even bigger than the magnetic tapes that we were talking about before. And so what these different images from my past serve to show is that computing has really accelerated exponentially, both in terms of processing speed, but also in terms of size as a result of that. And of course, we can see this quite nicely on this curve. We can go back to the UNIVAC that my grandfather worked on way back in 1952. And on this curve, I plot calculations per second per $1,000 that these different computers made. And back then, the UNIVAC was operating at about 1 calculation per second per $1,000. Today, we're somewhere up around 10 to the 12 calculations per second per $1,000. And you see this curve has been growing steadily and exponentially. And so, the reason why this is all important is, yes, it makes our computers faster, but it's also accelerated the pace of change in our society, right? So, years and years ago, we had the Industrial Revolution, but since that time, our technologies have accelerated so much and changed society, hopefully mostly for the better, that we can barely imagine the kinds of things that happened hundreds of years ago. Now, I'm not going to get into this singularity, but the notion is that we're growing so fast, our computing power is growing so fast, that at some point we're going to surpass the computing power of our own brains and perhaps even merge with computers. But I'm not going to speculate on that. Key point is that computing is growing exponentially fast and has been doing that for quite some time. But the problem is that exponential growth rate is not necessarily going to continue forever. And in fact, there are a lot of signs that that growth rate is turning around. So a lot of people call this the end of Moore's law. For those of you who are unfamiliar, Moore's law essentially states that the number of transistors per chip is going to double roughly every 18 months. And that's exponential growth, like I was showing before. And that exponential growth has gone on for quite some time, at least 5 or 6 decades. But the problem with this is that if you look at indicators of computing performance, you see that growth rate turning around. So on the right, I show a few examples. I show a plot of transistors per chip, clock speed, and thermal power design over the many different years. And you can see that while the transistors per chip are basically still growing exponentially, so linear on this plot means exponentially, the other metrics actually turned around about a decade ago. So thermal power design, clock speed have turned around. And so engineers have tried to find ways to keep these things growing, clever tricks. But the point of the matter is that some of these indicators of Moore's law are turning around. Part of the reason why they're turning around is because some of our transistors are getting so small that it's becoming impossible to deal with the heat that they release. And it's also becoming impossible to shrink them even further. So we think about the transistor sizes that have come out recently. So things like 10 nanometers, 7 nanometers, people are even thinking about 5 nanometers. Once you get to the scale of 5 nanometers, Quantum mechanics takes hold. So my day job is actually as a quantum mechanic, and I can easily tell you once you start reaching a few nanometers, that's when electrons start to tunnel in ways that you can't really control. So electrons are going to tunnel probabilistically. You can't direct them to tunnel or not to tunnel, and so that becomes very, very difficult to deal with within modern circuits. The other reason why this is problematic, besides fundamental physical limits, is because it's incredibly expensive to make things that are this small. So many of the fabs, the fabrication facilities that are being made today, they cost billions and billions of dollars to make, and so it has to be worthwhile to recoup all that spending to make these fabrication facilities in the first place. So the point of the matter is that these different turnovers are suggesting that we're sort of nearing the end of Moore's law. Of course, that's problematic because we just said that society has been accelerating as a result of the speed up. The other issue that we're combating today in computing is also big data. So big data helps us in so many ways. We get to learn more about the world and society, but big data itself is difficult to store. If you think about your everyday lives, right? We have phones. We have other devices that are constantly producing data. There's just so much data that we produce just by living that we never produced before. And so some people estimate, for example, that we use 4.4 zettabytes of data in a year across the entire globe, and that's accelerating to something like 44 zettabytes this year. That's an incredibly large amount of data. And maybe that would be fine if we could easily store it, but the problem is that our capacity to store data is not growing nearly as fast as our capacity to create data. So on the left, I show exabytes versus year, and the blue bars indicate how much data we really want to store, how much we're producing versus how much data we'd actually be able to store. So the orange bars are how much we'd be able to put on devices. And you can see that there's a discrepancy in the growth rate for these. So fortunately, both of these are growing. But as you might know by taking a trip to your local, here in the US, Office Max or Office Depot, you might realize that these orange bars aren't growing as fast as you might like. Technologies for storage haven't changed that much over time. And so we're missing all this storage of data. There are tricks. We can do things on the fly and not necessarily store everything. But at the end of the day, we're going to be missing a lot of things if we can't store them. And so these problems bring up the question, can we move beyond the current paradigm? Can we start thinking about other ways of, let's say, storing information, let's say, processing on that information that can relieve some of the issues that we're encountering? So can we find denser storage media? Can we find ways of computing that are more energy efficient so we can turn some of those curves around? And so if you think about the scales that I was talking about, transistor scales, when I'm talking about 5 nanometers, once you start getting that small, you might start to think about things like molecules, right? So here I show N2, our favorite triple bonded molecule in the air all around us, right? N2 is on the scale of angstroms, about an order of magnitude smaller than the nanometers that we're talking about. You can also think about things like anthracene. So anthracene is on the scale of nanometers. And DNA, look at the turning radius of DNA, we're talking about 3.4 nanometers. So these very objects, these molecules are exactly on the scales that we would want to actually be able to go smaller than transistors. And so that begs the question, why don't we try to compute and store information using these small molecules? And so this might sound crazy, but there actually are a lot of advantages to small molecules. So when I was a naive little theorist starting on this project, I thought about how much could we actually store in molecules. And here's an example. So let's say we have a flask of water, and we make the assumption, and I'm not saying this assumption is true or anywhere near this assumption, but let's make the assumption that we can store a bit of information in each water molecule. So just 1 bit per water molecule. And if we can store 1 bit of information per water molecule, you can do the calculation that a flask of water would be able to hold as much information as 200 Empire State Buildings worth of terabyte hard drives. So I like the Empire State Building just because I'm a New Yorker, grew up in New York my entire life. The Empire State Building used to be one of our tallest buildings in New York, not so much anymore. But the Empire State Building is a very, very big object. And if we wanted to store the same amount of information in a flash concorder, it would take 200 of these to do so. And so you can see that storing information in molecules is dramatically more compact than in our current devices. Like I said before, you can also show that performing different types of reactions requires less power overall, less energy overall than other types of computing. And you can also potentially imagine that all this computation is embarrassingly parallel. So I'll show you, hopefully if we get there, a couple of examples of parallel computation. But because molecules, let's say, can be distinguished from each other in unique ways, you can compute on different types of molecules all at the same time. So that creates a type of parallelism that we're not used to. And so all these different advantages suggest that maybe molecular computing could be an advantageous thing to do. Now, before I move on to what we specifically did, let me remind you that, of course, we're not the first people to think about molecular computation. In fact, if you think about yourselves, your bodies are massive molecular computers. Your bodies use molecules to do all the information processing that you need in order to survive as a living being. So, for example, if you think about DNA stores roughly 1.5 gigabytes of the human genome. And so we're talking about gigabyte storage. And obviously DNA is acted upon all the time by a variety of different enzymes. You can argue, like Charlie Bennett did in the 70s and 80s, that those enzymes are actually little computers, highly energy efficient Brownian computers. And so our bodies are showing that molecular computation is an effective strategy. We're here, we're surviving. Maybe we're not 100% optimal, but we do pretty well, and we're using molecules. Of course, people have also thought about doing DNA computing to solve problems, so not just to store information, but to solve real-world problems. And I'm just showing you a very old example by Len Edelman. Of course, Eric Winfrey and others have spent a lot of time trying to make DNA computing better than one could originally imagine. But way back when Len Edelman started thinking about these problems, he thought about using DNA to actually satisfy optimization problems. And so he wanted to solve the old traveling salesman problem, which had to do with trying to find, essentially what is the fastest route or the shortest route between two different destinations if you have to go through a bunch of different destinations. And he solved this problem using DNA by encoding the different destinations like Atlanta and Boston in DNA pieces, and then also encoding the, let's say, trips between them in DNA strands, and then throwing all those strands in and just letting them hybridize. So if you let them hybridize, we'll get double strands of different lengths, but you can pull out the smallest strand, and that's the answer to your optimization problem. So this showed that you can also do real computing using molecules. Now, what I'm going to talk to you about today is going beyond these paradigms. So I think we see why molecular computing might make sense. But what we're going to do is we're going to look at small molecules, so not polymers. We're going to think beyond the polymer box. And some of the themes that will come out is that small molecules lend themselves to unordered mixtures of molecules in solution, whereas large polymers are ordered. And so there are various trade-offs that accompany taking one type of encoding mechanism over another. What I'll also show you today is that in order to store all this information in small molecules, we also put a lot of pressure on the synthesis and the detection that we need to do. And so I think this is a common theme in all molecular computing that if we want to actually store information, we have to store a lot of different bits, and that's a lot of different combinations of molecules, or let's say bases in the case of ordered polymers. That's not easy to do from the synthetic standpoint or from the detection standpoint, where you actually have to read out all that information. And lastly, if I get to the computing part, I'll talk about what we believe to be our fundamentally molecular computations. So you can impress upon molecules or any other medium the digital computations that we're used to. We can try to make them do gates. But that's not always a natural thing to do. And so what we've been trying to do in this project is to think about what is a natural molecular computation. So what do molecules do every day that basically amounts to a computation that we can use? So rather than taking some construct that we've had to use in all digital computing and putting it on molecules, we try to ask what will the molecules give themselves. So that said, let me go into what our team has exactly been doing. And if this were live, I'd be happy to take questions on this and make this really into a tutorial. But hopefully you'll get enough information in order to help you realize this yourself or understand what's going on. So first and foremost, if we want to encode information in molecules, we have to think about what it really means to read and write data. And so I really like this figure from one of our papers because it reminds us of how ginormous this task is, even though our computers do it every day. So if we want to write information into small molecules, we basically have to write a series of bits. Of different digits. But if we're writing a series of bits, zeros and ones, a specific sequence of zeros and ones is basically going to be one of a large number of possibilities. This is sort of fundamental information theory. So if we want to write, let's say, n bits, those n bits are one combination out of 2 to the n bits of possibilities. So you have to be precise enough to get that specific bit sequence over every other. So if we're going to write that bit sequence to molecules, we can do this potentially in a variety of ways. But the choice that we wanted to make is to write those bit sequences into the presence or absence of molecules in a solution phase mixture. So in other words, what we decided to do is if we look at, let's say, bit position 1, we could write that into mixtures by saying that the first molecule is present or absent in that mixture. And then if we want to look at the second bit, we would say that the second molecule is present or absent in that mixture, 0 being absent, 1 being present, and so on and so forth. So just by the presence or absence of different combinations in a mixture, you could store information. Now, as you might realize, if we're going to store information in those molecules, the molecules have to be distinguishable from each other. So that first molecule is going to have to be different than the second molecule so that you know what you have in the solution and whether it's present or absent. So we can write these bit strings just by taking the presence or absence of combinations of small molecules. And that's a new concept. Our bodies do it all the time with things like metabolites. That's at least a new concept in our literature. We can store it in these mixtures. And if we want to read out that information, then we have to perform chemical analyses. And in performing chemical analyses, what we have to be able to do is we have to go back and extract that one bit stream out of the 2 to the n possible bit streams that could have been made. So that's a really hard task. I just want to impress that upon you. We have to have detection tools that have a high enough resolution, that are good enough to be able to pull out one sequence from all of those many sequences. So if you know chemistry, you can think of lots of different tools that can potentially do this kind of analysis, right? We can use lots of different spectroscopies. We can use mass spectrometry. We can use NMR. There are a lot of different tools. But because of that resolution, because we have to get every single bit of those many combinations right, what we ended up choosing is to go with mass spectrometry, because mass spectrometry could get the resolution that we needed. So I'm not trying to offend spectroscopists, but you can think of lots of common optical spectroscopies, for example, or you can think of lots of common IR or Raman spectroscopies, and you may realize that in solution, those are just going to be too noisy, too broad. Their peaks are going to be too broad to be able to distinguish all the different types of molecules in a solution. So to do this task, we use mass spec, and if we're able to actually read the stuff out, then we know if we can recover our sequence or data or not. So that's the basic idea. We're going to write information to small molecules and mixtures, and then we read it out using spectroscopy. So how did we precisely do this? So first and foremost, what we did is we decided to synthesize the molecules that we want to store information in. And I'll get to this in a second, but we use small molecules that have different R groups to allow us to synthesize in some sense combinatorially. So if we have molecules that have these different R groups and you put different R groups at different places, you can imagine making large different types of different combinations of these different small molecules to make them mixtures pretty readily. So we synthesize molecules to store that information. Then we use mass spectrometry, specifically an T-ICR mass spectrometer, to read out that information in the spectra. And then we performed a variety of different analyses to automate this and to recognize what's actually in these mass spectra. And so this is where the engineers came in. You know, we never really, as chemists, we never sit and think about automation as much as perhaps we should. But the engineers got this all really up and running and working wonderfully by their ability to automate all of the synthesis and all of this detection, the analysis that's related to the detection. And like I said, if I have time, I'll talk about the computation. We've been able to store lots of different types of data. As long as you can translate it into a bit string, which is pretty much true for everything, then we can encode and read that data out. Okay, so what are the types of molecules that we used? So our first guess was to say, hey, why don't we make some molecules that have a chemistry that scales combinatorially with the number of pieces you could put together in the molecules. So one such chemistry are actually multi-component reactions. And we chose the ULTI 4-component reaction because our team had some expertise with this reaction before. But this reaction is excellent because it really does get that combinatorial scaling. So in this 4-component reaction, as you might imagine, it takes 4 components, an amine, an aldehyde, a carboxylic acid, and isocyanide, puts them together into one ULTI product, which is also called an alpha acyl amino carboxamide. And if you think about these different R groups, we can have lots of different combinations of these R groups. But let's say we take 10 R1s, 10 R2s, 10 R3s, and 10 R4s. If you can mix and match all of those, then all of a sudden you have 10,000 final products. And so you can easily see here that just by being able to change these different groups, now you've got a very large number of different molecules. And so that's why we went with this system. Now, I should note that there's no reason why we only need to have 10 R1s or 10 R2s. You know, we can have 100 R1s, 100 R2s. A lot of these different R groups exist, and you can get them commercially. So there are a lot of different combinations of molecules that you can make. The other thing that was really surprising to me, so, you know, I'm sort of the silly theorist who's a little bit cynical. Like I'm optimistic about the things that we can do, but then I'm also cynical about things that have been done in the past. Very strange combination. But as a silly theorist, I thought, hey, you know, this is going to be a hard reaction to do, and it's not going to be that high yielding, especially if we do it at low volumes. I'll show you in a second. We're mixing these things at 2.5 nanoliter volumes, not very high volumes. I thought this would be very hard to do. But actually, our synthetic chemist, Jason Sello, who's now at UCSF, you know, he said, no. You know, this reaction is really high yielding. You put it together, it's going to make what you want. And in fact, he was right. I thought he was crazy, but he was absolutely right. These reactions are also something like a 99% yield. And so that makes us very happy because we can almost guarantee the fact that our products are being made. We don't have to do anything special. We can do completely automated synthesis and actually make these things to the yields that we need. The other obvious thing is that these are easily characterized by NMR, and of course they have masses, so that they can be characterized by mass spec. That said, how would you actually write information to these molecules? So I'll just give you an example. Part of the American Chemical Society here in Rhode Island, and what you can do is you can take any text. So let's say Rhode Island ACS. You can translate that into binary, easy to do, right? You can just do it on your computer all the time. And once you translate it into binary, you can take different molecules. So I took a bunch of skeleton ULTIs, and I showed where they can vary at different positions. And I showed 4 different ULTIs that you can make. Actually, with these ULTIs, if you took 2 groups per R position, you would really get 8 combinations. But actually even more than that. Anyway, if you took 2 groups per site, then you would get a variety of different combinations. But what we can do is we can say each unique molecule, so let's say molecule 1, could represent each position in this bit stream. So molecule 1, if it's present, would give us a 1 in the first position. If it was absent in the mixture, it would give us a 0. And then we can do the same thing. Molecule 2, if it's present in the mixture, then you get a 1. Otherwise, if it's absent, you get a 0. And you can do that for the entire bit stream, mapping it to the presence or absence of all these molecules. So that's the basic idea. I'm giving you the kernel of the idea. But of course, if you did that, you'd have lots and lots of molecules. Just to write Rhode Island ACS, right? This is going to be like 100 molecules. And so you see that the scaling of that, isn't perfect. And so I'm not going to go into a huge amount of detail today, but we've used a variety of schemes so that we don't have to do sort of a 1 molecule per 1 bit kind of analysis, so that we can get we can end up with more compact representations of that, which really helps on both the synthetic side and then also on the detection side. Okay, another factor to consider is aside from having to make all these different molecules, if you're going to do essentially 1 bit per molecule, is the fact that in order to read out these molecules, put too many molecules in 1 mixture, it's going to be a hard task to read out all that information. So originally I was thinking, okay, why don't we put all this stuff 1 pot, 1 mixture, and you can imagine if you were going to store 1 megabyte, that would be something like 800 million molecules. Okay, that's pretty crazy. I'm throwing out how we would make this information more dense, but let's say we did have 1 bit per molecule, that would be 800 million molecules. And so what we realized is to make our lives easier, what we can do is split up these mixtures into smaller mixtures. So for example, we can take 25,000 smaller mixtures that we can put in separate wells. And if you do that, then your detection task is easier, then your synthesis task is easier too, because each well will store its own information, so you can use the same kind of molecules from well to well to well. And so this was a very profitable realization, and we were able to do this, this really simplified our task overall. So that said, what we decided to do is do a lot of this on well plates, 1536 well plates that you can just order for biological tasks. And when you make these OOGIs on different well plates, you can take the different components, so let's say an amine, and just plate a plate of all, just take 1 amine and plate the whole thing with that amine. If you had to incorporate 2 aldehydes, you take half that plate for 1 aldehyde, half that plate for the other aldehyde. And you can make stripes and other patterns on the other plates, and then mix these all together to make all the different compounds. Now, when we were first doing this, I had a new graduate student, starting my own group for the first time, and he used to be a synthetic graduate student. And so I asked him, hey, could you help us prototype all of this? And so Len's a good guy, and he said, yes, I'll help you out. If you want to store information properly, you have to get the precise combinations of all of these different components right. So, he was working with another student who was on our project for several years, Amanda, and, they would sit in a corner of a room, and Amanda would say something like, mix A1 with B6, with G8, with H10, and then Len would hear something like, mix H1 with B17, with C6, et cetera. And you can imagine how problematic that would become, because if you're storing information, you have to synthesize exactly the things that you intend. So suffice it to say, Len hasn't done any synthesis then, he just does computation in my group now. He ran screaming and yelling for good reason. If you had to actually store all the information that way manually, it would basically be impossible and horrific. And so the engineers started to get smart. We started to think about how do we automate all of this. And we ordered 2 really nice friends. So on the left here, you see our friend Andrew Robot. He's an AI, and he pipettes. And he pipettes pretty accurately. I mean, he doesn't always know where the plate is, but as long as he does know where the plate is, he'll pipette and get those sequences right. So we automated Andrew to do a lot of our smaller syntheses for us. But then we also graduated even further up to an acoustic liquid handling machine, the LabSite Echo. And this has really, really saved us. So this is a great machine. What this machine does is it essentially uses acoustics to launch little droplets. And when I say little droplets, something like 2.5 nanoliter droplets from one location to another location. So, you have a plate below, you have a plate above, and then you'll be launching droplets from the plate below into the plate above in different positions. And so this was a huge benefit. I cannot say, I cannot overestimate how much this helped us, because this machine can do something like over 100,000 liquid transfers per day. So that's extremely important if you want to, first of all, synthesize all these molecules, and then second of all, then mix them into mixtures. And so this has been a fantastic thing that we program and we automate to do all the syntheses that we need to do. Well, like I said, we then were able to read out all of these different mixtures using mass spectrometry. We were lucky enough to get a Fourier transform ICR mass spectrometer. This is a heck of a machine. What it does is it basically is able to read out the masses of molecules that are suspended in orbits by magnetic fields. So it's just using Lorenz's law. And it can suspend something like 10 to the 6th masses at a time, which is pretty amazing. So that means that essentially you could, in fact, in principle, measure something like 10 to the 7 different molecules in solution at once. And so you can see how useful that is if we're looking at mixtures that have large amounts of molecules. This machine also has an incredibly high mass resolution, something like 10 to the 6th, a large mass range. That means we can look at a whole solution, but still be able to read the masses down to fractions of Daltons. And I'm not showing you this today, but you can do the simple calculation that says if we were to read these, if we're going to make all these different masses, a lot of the masses are going to fall very, very, very close to each other. So if you only had, let's say, 1 Dalton of mass resolution, you'd be in a heck of a lot of trouble. You wouldn't be able to read very much. And so you really do have to get those small masses to basically read any of the molecular masses that come close to the unit masses. So if you think about it, you can do this exercise that most molecular masses are not going to span the region between units, but they'll span the region right around each individual unit. And so you have to have high resolution to get those little masses around each unit. Okay, so all that said, what's our workflow? So we would take our data, and when we had our data, we would map that data, obviously, into binary. And then once we had the binary, like we showed before, then we would map it into small molecules. Once we would map it into small molecules, we would make those small molecules. So we do this robotic library synthesis. And we can either make those molecules on the fly, or we can sort of store what are the molecules that we're going to use as a library. Once we have those small molecules, then we can make our mixtures based on exactly what we're encoding. We can use acoustic MALDI to spot plates so that we can actually read them out using the mass spec. And once we read them out using the mass spec, we can perform different types of data analysis. So that seems straightforward. And maybe, again, if you're the silly theorist like me, you would have said originally, oh, there should be 1 mass per molecule in your mass spec. If we had a lot of molecules, that'd still be a lot of masses. But the thing is that you don't get 1 mass per molecule in your mass spec. In other words, you don't get 1 peak in your mass spec. You actually end up getting lots of peaks for every single peak in your mass spec. So here's an example mass spectrum. We're just doing it for 1 compound that we made. And what you see are there are a lot of peaks. And these peaks are coming from different isotopes. They're coming from different ions that interact with the mass. So a lot of the masses will become sodiated or potassiated. And these ions just come from things like glassware in the environment. And these masses will sometimes also interact with the matrix itself and different combinations of the molecules that make up the matrix. And so you get a lot of different peaks. And so, you can imagine that this could fill your spectra with a whole bunch of stuff that you don't need that's kind of repetitive if the peaks were exactly in the same position. So we thought this was problematic for a while. If you think about what this translates to, so if we, let's say, have a 32 UGI data set of bits, we wanted to encode that. Now we got to encode lots of these different bits. They all come with their own different peaks. And so now our spectra get even messier. But what we realized is that we could actually use these different peaks to provide us with further information. So instead of searching for, let's say, one peak each time, what we can do instead is we can train some algorithms, some ML algorithms, to search for the most discriminatory peaks for any given set of mixtures. So, why do that? So, like I said, there are many peaks, but it's also from mixture to mixture, set of reactants, but set of mixture molecules to set of mixture molecules, different peaks are higher than others. And so which peaks will have which intensities will fluctuate. So what it's better to do, we realize, is to train our machine learning algorithms to learn which are the most intense peaks for a representative set of mixtures. And then with those discriminatory peaks, go and figure out what's in all the other mixtures. So here I show an example from one of our papers where we actually stored information using metabolites. So I told you about ULTI molecules, but in fact, you can store information using any small molecules. They just have to be distinguishable. And so we stored some information using metabolites, and we looked at the detection accuracy of different peaks that represented different molecules. And let's say in one situation, you could find that the sodium peak is the tallest peak, the most intense peak for a given molecule. We can take those combinations of let's say, the sodium-like highest peaks, and then we can use them in a discriminatory algorithm to figure out what's actually in the different mixtures. So let's say we can take the 10 peaks that have 100%, close to 100% detection accuracy, use those peaks to discriminate everything else. And if you do that, if you see the figure by B, you can see that we significantly lower our decoded error rate. So if we use just a single peak to read out our spectra, our error rate is something like a few percent. We use multi-peak detection, like I was saying, where we don't make any assumptions about what peak is going to be most intense. Then we bring down our error rate significantly. And so with that, we've been able to encode images with over 99% accuracy. We're not aiming for 100% accuracy. We're trying to head in that direction, but we don't need 100% accuracy is my point if we're able to do error corrections, if we're able to encode our data cleverly. And so we've been using lots of different techniques, such as that multi-peak discrimination, in order to encode our information in ways that we can correct, in ways that will facilitate detection. Another scheme which I was alluding to before that we've used is also using data sparsity. So like I said, if you wanted to store information with large numbers of bits, then you have many combinations of those bits. And if you did this in a very dense way where every single bit is directly represented, then it would be very hard to distinguish a mixture that has an error from a mixture that does not. And so instead, we decided to use sparsity to rewrite these really dense bit streams into sparser bit streams that only have bits in a few possible positions. And so this makes it easier to figure out if you actually have an error or not, and to map what you're reading out to the actual data that you expect to get out. So we've used all of these tricks, and we stored a variety of images. If it were up to me, we'd probably store much more fascinating images, but the engineers were into Egyptian tapestries, and so we stored things like ibex. And here's ibex. We would basically translate ibex into different data vectors. Then we would permute those vectors so that if we make any mistakes in reading out the information, that those mistakes are not all in one spot, so you don't get one big mess up in your image. We decode that into chemistry and read it out using the MALDI, and then we would get our images out. And so you can see we have a couple errors in these images, a couple of black dots on the side of our ibex. But we would get this in very high accuracy, and because we used a lot of different encoding tricks and permutation matrices, these errors would be in different positions. So we basically have the image right. So we've done this for lots of different things. Most recently, we did Picasso's The Violinist, and these images go up to basically megabytes of data at a time. So I'm showing some of our older images, but these are all fairly large images, all encoded using molecules, all detected with greater than 99% accuracy. So what does that say? Where are we actually with all this? So in blue, I show some of our group's works using these small molecule mixtures. And only a couple of years of work, we've really been able to store information in this megabyte to gigabyte regime that people have also stored, stored information in DNA. And so our small molecule mixtures in that short period of time have gotten to the point where we can store really a large amount of information in molecular terms. Now, you would obviously say, looking at this chart, yeah, people have stored more information in DNA than we did. Yes, that's right, but we've only been working on this for a short period. And we haven't actually, in the past couple of years, we haven't been pressing as much on the information storage now that we've realized it, that we've shown that this is all possible, it's easy to do using mixtures, and we've shown the basic theoretical principles. What I'll also point out to you is we did this using the UGI products, like I said, but we also did it using metabolites. And again, you can use any set of molecules, and that's a really powerful concept. You don't have to synthesize specific types of things, as in other types of molecular storage approaches. You can really take any molecules off the shelf, and as long as you can distinguish them from each other using a mass spectrometry in our case, then you can use those molecules. So you don't have to do some crazy expensive synthesis to do this. You can really order a collection of molecules or just get them from wherever and use those to do the storage. So that's also a really nice principle. Like I said, we haven't been pressing as much on the encoding and the storage recently. We've been focusing more on computing. But part of the reason why we decided to change directions a little bit is that we did some calculations for how much we're writing over time and how much we've been reading over the time. And what we see is that our primary limitation is how fast we can write. So if you look at the plot on the bottom right, bits per second over time that we've been able to write information. Blue curve shows that we haven't been able to write information as quickly as we've been able to read it. And you might have expected that from my previous description. When I was talking about writing information we had to synthesize, I was talking about reading. We use that mass spectrometer to read a whole bunch of bits all at the same time. And so we've been able to basically read whatever we've tried so far. But to write requires a lot of liquid handling, right? We have to actually make all the molecules. And even if we synthesize those ahead of time, it still requires a lot of moving of droplets. Once we make those molecules, we have to mix them into mixtures. And so to make all the different mixtures, you also have to do a lot of liquid handling. And that's that fundamental moving around of the liquid that is taking us the most time. And so I think this is a common problem throughout synthesis, and maybe smarter people among us should be thinking about how we can make molecular bits faster than we are now, because that seems to be the bottleneck so far. And I know there are companies like Twist that are thinking about this, but this is a general concern. How fast can you actually make these things? So we haven't been pressing on this because we're not going to design our own printer to do this right now. But if we wanted to, in fact, we could. Okay, last thing before maybe I talk a little bit about computation. We think that this notion of storing information in mixtures is actually a new theoretical paradigm. It's not new practically, but it's new in the way that we think about information storage. So I know I've recently been reviewing different papers about polymer storage, and they don't even realize that these combinations, like this is the first time that they ever thought that maybe combining different DNA strands, in their case, synthetic polymers would actually give you different amounts of information. But the basic idea is that we realize that there are essentially two kinds of paradigms that you can think about, two extremes. One extreme is that you can store all your information in the length of the polymer. So that's going up this y-axis. You can take a few monomers and then just make your polymer really long. And then you get a large amount of information storage. Or you can move to the other end of the spectrum that we were on. We can increase the number of monomers that you have and mix those all together in a disordered way. And that can also increase your information capacity. So you can either have these really long monomers, or you can have just many monomers that you all put in solution. Either way, you increase that storage capacity. And so you can think about approaches that combine these two things. So you can take ordered polymers, and then you can make mixtures of the presence or absence of those ordered polymers. And that would increase your capacity, these gray diagonal lines, even further. So we think this is a new notion. I think people generally have been thinking along this polymer length axis and not so much about the diversity of monomers that you can put in unordered mixtures. But you can really use both, and that will increase your capacity overall. And I think it's fruitful for people to start thinking along those directions, how we can marry the two, because that's certainly what our bodies do. Our bodies use both in small molecules and the long biopolymers. Okay, so that was storage. I don't want to take up too much of your time, but maybe I'll just give you a couple quick glimpses into computation. So one of the main tasks that we've been going along in terms of computation is trying to realize machine learning algorithms in chemistry. And the component of machine learning algorithms we've been working on is the perceptron. And the reason why we've been doing this is a fewfold. First and foremost, if we're able to realize machine learning algorithms, those algorithms allow for us to realize essentially universal computation. So that's been proven, that machine learning can realize universal computation. The second reason for doing this is what I realized early on in this project is that actually molecules can perform certain operations really naturally, even though we never think of them as doing so. And one such operation is the multiply accumulate operation. So this is the operation where you multiply a bunch of inputs by, let's say, weights or other numbers, and then you accumulate them all. And so in chemistry, we do this all the time, actually. So in chemistry, we take different concentrations of things, and then we let those things react, and then we pool all those things together. So the pooling is the accumulate. The multiply is letting things react according to their different concentrations. So chemistry does that quite naturally. Almost everything in chemistry does multiply, accumulate. Chemistry also does things like thresholding. Maybe I'll get a chance to show you very quickly, but you can use autocatalytic reactions to threshold things. They can serve as activation functions. And so if you recognize that chemistry does these things naturally, then you could say, oh, these components, the multiply, accumulate, and the thresholding, they go into machine learning. I mean, they make up the fundamentals of machine learning. And so I recognized this early on, and so we decided to go down this route and to realize a perceptron. Perceptron you can think of as a binary linear classifier. What it does is it takes in, let's say, a bunch of text or images, and then it classifies those inputs into one of two categories. And so in the case of animals, you can throw in a bunch of animals, and those animals can be classified as either cat or dog. Perceptron is going to do that for you. And to realize a perceptron, you just have to evaluate this Z I'm showing here as a multiply accumulate of inputs by their weights. And you can also add a bias here. And then this Z can be thresholded to say, is that Z large enough to classify the inputs, the Xi's, as one category or another? So we can entirely represent all these operations using chemistry, like I said. And what we chose to do as a first example, and I'll tell you, this example is probably the most automated example, but we've since done all this in chemistry, is that we can represent this multiply accumulate by taking concentrations of molecules and weighting them by the amounts of those concentrations that we basically volumetrically move into one collective pool. So in other words, we can realize this multiply accumulate by taking concentrations of species and then simply volumetrically moving them all into a pool according to a volume that represents the weights of those species. So that's our chemical multiply accumulate. Again, we can do this all in chemistry now, but I'm just showing you our first example of volumetric perceptron. And we decided to do this on a bunch of different images. So as many of you know, a lot of people will test machine learning algorithms on different images of things. And so we decided to use really, really small versions of MNIST images, images of numbers like 1, 2, and 3, and then different letters. And what we can do is we can encode these different numbers and letters in different analytes, so different molecules. And what is unique about this, and what's unique about the chemistry, we talked about parallelism, is that we can do this all in parallel. So we can encode these different numbers on well plates, just like the well plates we were using before to store information. And because these are represented by different molecules, we can pool all these molecules into the same well plate. and then perform our machine learning all at the same time, and apply our perceptrons all at the same time to all these solutions. And so that's a uniquely parallel thing that we can do in molecular computation. And while I won't show it here, you can show that it requires far fewer molecular operations to do this than in silico. So the scaling is much better in terms of operations for doing this. Once we have these images, what we can do is we can train our perceptron. We can do that in silico. We can figure out all the different weights that we need to recognize whether these different molecular images represent, let's say, a 0 versus a 1 versus a 2, etc. So we can form these different images. We can put them into the same well plate and then analyze in parallel with weights that we've trained whether these images represent any sort of digit. And if we apply these weights and perform the volumetric transfers to represent those weights, we can pool them in separate positive and negative pools. Turns out that we need those separate positive and negative pools because we don't have something like negative concentrations in this example. That's a key point. I'll return to that in a second. And once we have these different pools, then we can threshold them. So we were using HPLC to set thresholds for how much we actually need of these different components. And once we decide whether these have surpassed thresholds or not, then we can classify whether the individual images were what we trained the network to recognize or not. So this is what we call our volumetric perceptron. And once we did all of that, on the right, I show a couple of examples. What you see is that we were able to get greater than 96% accuracy doing this. So on the right, I show that we encoded, let's say, 3 different images, 2 zeros and a 1. And then we trained our weights separately again to recognize a 0, a 1, and a 2. And we can apply these trained weights to all these images put into one well plate in parallel, and then see, once we apply these different weights, do we actually recognize a 0? So in the first row, you can see that, yes, we recognize a 0 twice. And then when we apply the 0 to the 1, we don't recognize a 0. So we get that right. And then you can also do that with the 1 weights. We can see if we recognize a 1 in these different solutions. And yes, we do that for the rightmost column. And so we were able to show that we can do a molecular perceptron. Of course, many of you might be saying, this is volumetric, right? Where's the chemistry? You're just representing things in molecules or storing things in molecules, but you're not actually doing the operations in molecules. But suffice it to say, I don't want to take all of your time, we can now realize our multiplications and, of course, our accumulations completely chemically. One way to do that is that we can take a molecule. Let's say that molecule has a specific number of moles. And then we can react it with 2 competing molecules. These molecules have reaction rates that are essentially the same. And these molecules, because their reaction rates are the same, they're probably very similar. And so we can react our one molecule with either of these 2 competitively. And if it's competitive, the amount of this molecule times the amount of, let's say, the first will tell you the amount of the final product of those 2, Y1, that you get out. So in this way, you can multiply different concentrations together to get final concentrations. So we can do that multiply completely chemically. And for the sake of time, what we can also do is that thresholding completely chemically. So you can imagine one possible nonlinear threshold is a sigmoid. And a sigmoid is exactly what you would see if you actually ran an autocatalytic reaction. So in an autocatalytic reaction, you start with some reactant. And then it starts to produce product, and that product comes around and actually helps facilitate, it catalyzes the formation of more product. So over time that ramps up, and you get a sigmoid that flattens out at the end because at some point you're using up most of the reactant. And so we also have realized that part of the perceptron, the thresholding part, via these autocatalytic reactions. So we've put all these different components together in order to make different machine learning algorithms. And right now, what we're working on is really making larger and larger machine learning algorithms that are deeper, have more layers, and represent more things. What I'll impress upon you is that we've been trying to realize all of this in chemistry, real chemistry, and we've been trying to use the natural operations that we find in different reactions to make these things possible. So that all said, I'll just summarize for today, and maybe someday I can give a computing talk where we can talk more about different computing motives. But suffice it to say, what I've shown today is that you can in fact store information in small molecules, and the amount of information you can store is quite competitive with what you'd see in DNA. Small molecules are nice because they're extremely dense, they're discrete, they're stable. I didn't talk about their stability, but they don't really react with enzymes because enzymes were not evolved to catalyze them, and so they are very stable. These different storage motives actually open up the possibility for parallel computation and other types of computations that we haven't thought about before. In particular, these computations will be very energy efficient. And right now, we're trying to think about how can we make these molecules perform even more complex computing tasks than the kinds of classification that we talked about today. And so one of our current focuses is really to say, can we find ways of making reactions perform real calculations? So I recognized early on in this project as the theorist that we can do a multiply accumulate, we can do some thresholding using chemistry. Those are natural operations, but can we put these things together in even more natural ways that can perform real functions in the lab? Because so far we haven't been coming up with a large theory of computing that if we had, let's say, these reactions, they're going to be able to compute X, Y, and Z for us. There's no overarching theory for that right now. I have a lot of ideas, but there's no overarching theory. And so in the past, we kind of made certain operations work for us. But there was no sort of directionality that we're going to move in this direction to systematically create computations. And so that's exactly what we're working on now. But that's also the point where people like you, young people like you, could really help. We really do need a theory for how to do this. There have been some theories in the past. I don't want to go into all the details of those theories, but let's just say they're not very practical. They don't think about any real chemistries that I've ever seen. And so we really do need theories that show us how to compute that are grounded in real reactions that happen on an everyday basis. All right, so with that said, again, I'd like to thank my team. This was a team that was funded by DARPA over the past few years, and we have a couple of years to go. We were led on the synthesis by Professor Eun-Suk Kim, also Jason Cello in chemistry, and then I got a huge amount of help from many of our engineers, so Professor Shirley Freda, Chris Rose, Jacob Rosenstein, who really automated and helped us with all the information processing tasks. And then Professor Peter Weber was really helpful in telling us all about mass spectrometry. He was the one who made the bet that the T-ICR would serve our needs, and of course it has. It's even better than our needs. We also had many fantastic students and postdocs work with us over the years. Chris Arcadia, who's now Dr. Chris Arcadia in engineering, continues to work with us, has done a great job. Dr. Eamon Kennedy, who's now, I think, a research assistant professor at Utah. They both did fantastic work on all of this. If it weren't for them, we wouldn't have these different papers. I should also thank my group. So, actually during the day, I do a lot of electronic structure and computational biophysics. But I had a few group members, namely Dr. Yuan Liu, who's now at Harvard MIT, Mr. Ben Foulon, who have helped a lot with this project, helped me think about the project, helped their team write different papers. And so they were willing to go on this crazy adventure to try to think about molecular computing instead of the opposite, computing on molecules like we usually do in our group. And so they've been a lot of fun. So with that, I'd like to thank you all for your attention. Again, I really appreciate it given all that's happening in the world today. I know it's been hard on me. It's probably been really hard on you. But I'm glad that you're all here, and I'll be happy to answer any questions that you might have during the live session. So thank you again.